Okay, in this lesson, we're going to be learning about real zeros of polynomial functions. We're going to review how to use long division and synthetic division to find the factors of a polynomial. We're going to be looking at three other theorems: the remainder theorem, the factor theorem, and the rational roots theorem. In a previous lesson, we talked about finding the roots of a polynomial function that is in factored form. So what happens if it's not in factored form? What happens if it's in standard form or something else? So that's what we're going to tackle in this lesson. So we're going to start off by reviewing how to divide polynomials, how to find those factors. We're going to start down here in example C. We're going to start with long division. So we've got 2x to the fourth minus 3x cubed plus 5x minus 1. And all that is divided by x minus 2. So with long division, we're going to start by putting that denominator outside of our division bracket, and then we're going to put everything in our numerator underneath it. Okay, notice that it's already in descending degree order. Also notice that we're missing a quadratic term, so don't forget to put in your zero terms when needed. Gotta have those placeholders. All right, so then just like with dividing long division with constants, we're gonna look and say, well, what can I multiply by this to get this first number, this first term here? Okay, with polynomials, we look at our leading terms. So we say, what can I multiply by x to get 2x to the fourth? Well, for this first round, we need a 2, and then we need 3 more factors of x. So we need 2x cubed. We're going to take that and we're going to multiply it by our whole binomial on the outside. Okay, so we get 2x cubed times x, which is 2x to the fourth, and 2x cubed times negative 2, which is negative 4x cubed. All right, and then just like with long division with numbers, we're going to subtract. Okay, make sure that you put parentheses around your binomial in that row to make sure that you subtract both terms and not just the first one. All right, we should always get a 0 for this first term, and then keep change, we get a positive x cubed. Okay, we're going to bring down the next term underneath our division bracket, even if it is a 0. And then we're going to repeat the process. We're going to say, what can I multiply by x to get this leading term? Well, I need 2 more factors of x, so I've got an x squared. And then we're going to do the same thing as we did last time. We're going to multiply this x squared by x minus 2. So we get x cubed minus 2x squared, and subtract. All right, and we're going to keep going until we get down to a constant or a 0. Okay, and when we get down to our constant, there's no polynomial we can multiply by x to get any constant. This one specifically is 17, so that's our remainder. If we were in elementary school, we would just put a capital R and then a 17, but we're not, so we say plus, and then we say 17 over whatever we're dividing by on the outside of our long division. All right, so our solution is 2x cubed plus x squared plus 2x plus 9 plus 17 over x minus 2. All right, to check that, we're going to use synthetic division. So synthetic division is nice and convenient for specific cases of doing polynomial division. Okay, so specifically, as long as we're dividing by a term that looks like, x minus c, then we can use synthetic division. Okay, so it's got to be a linear term, one coefficient in front of the x, and then we're just subtracting some value c. All right, and we're going to take that value and use that as our first number in synthetic division. Okay, for this problem, since I'm going to do the same problem, 2 is going to be our c value. All right, so I'm going to take that 2, and I'm going to put it up in our attic. And then with synthetic division, we just use the coefficients of each term in our polynomial. Okay, and we drop the variables and their exponents. All right, it's really important that your polynomial is in descending degree order and you've got any zero terms included when you list your coefficients. Okay, so I've got 2, -3, 0, and 5. And don't forget the constant, -1. Okay, so once we've got that listed, we're going to draw a horizontal line underneath it. And we're going to drop down our first term, that 2, underneath the bar. And then we're going to multiply that term by the number in our attic, our C value. Remember, this is our C value. All right, so 2 times 2 is 4. We put that in the next column. And then we add these two. Keep in mind, synthetic division, we're using addition, whereas long division, we're using subtraction. All right, so 1 times 2 is 2. Add up that column, multiply that sum by our attic number 2, and keep going until you get to the end. Okay, when you get to the end, I like to block off this last term because that's our remainder. If you notice, that's the same value that we got when we did long division. And so we don't want to leave our answer like this without any variables. It just looks like a list of numbers. So we want to rewrite that as a polynomial. I like to write it from right to left to make sure that I get my degrees right. So we start with that 17, and that's our remainder. So we put it over the x minus 2 that we were dividing by. And then we go to our next term, which is going to be our constant. Then our next term is our linear term, 2x. And then moving to the left, our quadratic term, and our cubic term. All right, and if you notice, that matches up with what we got when we did long division. All right, synthetic division is going to be real useful when we start to use it to find the factors and the zeros of these polynomials in standard form. All right, in your notes, if you would, practice long division with example 1, parts A and B, and practice some synthetic division with example 2, parts A and B for our next class. All right, so looking at our first theorem, we've got the remainder theorem. It says if a polynomial is divided by x minus c, then the remainder is the same as the function value f of c. Okay, so again, looking at dividing by some binomial, so we could do synthetic division in a problem like this. We're going to call this polynomial that we're dividing into f of x. All this theorem says is that if we just want to know what the remainder is when we do division, then we can just evaluate our function at that c value. All right, so let's go back to that same problem we were just working on, and let's see if we get the same remainder that we got with long division and synthetic division. Okay, so if I call, let's see, if I call our top polynomial here, that's our f of x. So if I evaluate that for f of 2, what we should get is this 17 down here that we got as our remainder when we did long division. Let's see what we get. Okay, so plugging in 2 everywhere we see x, we get 2 times 2 to the 4th power minus 3 times 2 cubed plus 5 times 2 minus 1. We'll give ourselves a little bit of space here. All right, 2 to the 4th. Let's see, that's 8, that's 16. 16 times 2 is 32. 2 cubed is 8, times 3 is 24. That's 10, take away 1. All right, so doing our arithmetic, we get 8, add 10, take away 1, that's 18 minus 1, so we do get our 17. All right, so it checked out. So now notice this only gives you the remainder. It does not give you the rest of the solution if that's what you're looking for. So why would we want that? What value does that have? Well, we got to look at our next theorem to see why that may or may not be important. All right, the factor theorem says for a polynomial function, x equals c is a zero of a function if and only if x minus c is a factor of the function. Okay, so we talked about this in and not as formal of a definition when we talked about the factored form of a polynomial and how to make the connection between the equation and its roots. But we can connect this to the remainder theorem in saying that if we use the remainder theorem on a function and we find out that the remainder is 0, then that c value has to be a root of that function, and x minus c has to be a factor of that function. All right, so let's look at example 4, part A. It says, use the factor theorem to determine whether the first polynomial is a factor of the second. Okay, so this here is our f of x, and our c value, again, we've got that built-in subtraction. Our c value is 1. So we're going to see what is f of 1. Now we could do long division, or we could do synthetic division, and that would be totally fine. We could get the same thing. But when we get into the higher order polynomials, or ones that have just a lot of terms or big coefficients, this is just a quicker way to test to see if a certain c value is a 0. All right, so plugging in 1, we get 1 cubed minus 1 squared, add 1, take away 1. Okay, so 1 to any power is 1. And so we get 0 plus 0, which is 0. So with the remainder of 0, that means that 1 is a factor, or 1 is a, let's see what the first polynomial, so 1 is a root, which implies that x minus 1 is a factor. Okay, in your notes, we do example 3, A and B, to practice the remainder theorem, and example 4, problem B, to practice the factor theorem. All right, example 5 we will do together next class, but I want to look at example number 6. Okay, it says completely factor this function f of x, use the graph below, and synthetic division. Okay, so we're going to have access to our calculators, to our graphing calculators for this unit, in order to graph some of these polynomials. But when you're asked to find these real zeros or complex zeros later on, we're looking for exact zeros, these exact solutions. If we have decimals, or if we have irrational or complex numbers, our calculator is not going to give us those exact values. Okay, so we're going to need to be comfortable with synthetic division and using a combination of that and clues from our graph in order to factor a polynomial and find all of its roots. Okay, so we're going to start with this one. And looking at this graph, this root right here, it looks like a -2. And let's see, this one here looks somewhere between 0 and -1. I'm not sure what that is. And this guy looks like it could be a +1. All right, so I want to test those first. And I'm going to test those by going back to synthetic division. All right, so I'm going to look at this -2 first. I'm going to go from left to right. And that's my c value. And then I'm going to take my coefficients. We're already in descending degree order. We don't need any 0 placeholders, so I'm just going to list those coefficients. And see what we get. All right, so we got 0 as a remainder. That's a good thing. That means that -2 is indeed one of our roots. So then the next thing I want to do, let's see, maybe let's go ahead and start our factored form of this. All right, I'm going to write it right up here. So we've got f of x equals, and let's see, my first factor is going to be x minus a -2, or we can just put x plus 2. All right, and let's test and see if this 1 is an actual root as well. All right, so I'm going to take that 1. And now here's the key part. When we have these higher order polynomials, in order to find these roots, in case they are irrational or in case they are complex roots, we're going to need to use the last row from the synthetic division from the last time we found an actual root. Okay, so what I mean is I'm going to take this last row, and because we've, in a sense, we've factored out this x plus 2, we can do synthetic division, with this last row, and now we have one less term on the top, but we're still looking to see if x minus 1 is a factor of this polynomial. All right, so it's really important that you use that last row the next time you use synthetic division. All right, so let's work through this. So we bring down that 3 times 1, it's 1 times 1. All right, we find that is indeed another root, so we've got x minus 1 is another factor. So now we're left with just 2 terms in our last synthetic division. And so remember, this represents a polynomial, which is 3x plus 1. All right, and that's just a linear polynomial. So when we factor it, we want to factor our polynomial down to just linear factors. So we can leave it just like that, 3x plus 1, and that's our linear factor. Okay, if it was a quadratic factor, we could have even done this up here at this step. Then we could solve that as just like it's any other quadratic equation. You can use quadratic formula to get, or completing the square to get those exact roots. Okay, if we were to be asked to find the roots instead of the factors, we still haven't found that root right there, then we would just take this and set it equal to 0 and solve. Okay, so subtracting 1, dividing by 3, we would find that that root is exactly at -1/3. Okay, but this is what we're looking for right here. All right, so one more theorem, and before we get to that rational roots or rational zeros theorem, just a reminder that if x equals k is a solution, we can also call it a root, we can also call it a 0, and we can also call it an x-intercept. This applies to any real roots, any real solutions. Our complex solutions aren't going to show up as x-intercepts, but otherwise all of these statements are equivalent. Okay, and then we just talked about that if k is one of these, then x minus k is a factor. All right, so rational roots theorem, rational zeros theorem says if we have a function f of x, then we can find the possible rational zeros. Okay, note this is just for rational real zeros by looking at the divisors of the constant term and divisors of the leading coefficient. All right, and we call P the divisors of the constant term, Q divisors of leading coefficient. Okay, so if we look at this example here, example 7, the last example we'll do together, it says list all possible rational zeros of the function. Okay, so we've got this f of x here, this leading coefficient is where we get our q's from, and this constant is where we get our p values from. All right, so we're going to kind of walk through the steps in order to find our rational roots and eventually any of the roots of this function. Okay, so p, looking at divisors of 10, that just means any number that goes evenly into 10. We want to consider pluses and minuses. So plus minus 1, 2, 5, and 10. And from Q, we're looking at 6. So factors of 6, 1, 2, 3, and 6. Looking at the positive and the negative factors. Part C says list all possible rational roots, P over Q. These are the only possible rational zeros of the function. All right, so I'm going to kind of have two lists. I'm going to have my positive values and my negative values. And again, we need to look at every possible combination of P over Q. Okay, so I'm going to start and I'm going to try all of my P's with the first Q, then all my P's with the second Q, and so on, and make a list. All right, so 1 over 1 is 1. 2 over 1 is 2, and so on. Okay, these are all my negatives. I'm going to just write this out front to save making a whole bunch of messy negatives. 10 and negative 10. All right, so we've taken care of this guy. So now I'm going to do 1 over 2. 2 over 2, which is 1. We've already got that. We don't need to write that again. 5 over 2. 10 over 2, which is just 5. We've already got that. We don't need to write that again. So we've taken care of the 2's. So now we go to the 3's, 1 over 3. Okay, so long list of some messy fractions. On the second half, we've got all of our possible rational roots for this function. So there are no roots that can exist that are not in this list that are our rational roots specifically. All right, so part D says graph the function to see which are the zeros of f of x. All right, so this is the part where our graphing calculator comes in. You would type in your f of x and get a visual of what that looks like. All right, so here's what our f of x looks like if we graphed it. And notice we've got a root here. Looks like it's somewhere between -2 and -3. A positive root here between 0 and 1, and then another positive root that looks like could be at whole number 1. Okay, so now we're kind of at the same spot as we were in the previous example, where I want to test these algebraically to see if they are indeed roots. So that 1, I'm going to test that first because that's the only whole number it looks like we've got. Okay, so doing part E, I'm going to use that 1 to start off, and I'm going to pull my coefficients from my f of x. So I've got 6, 5, -21, and 10. And we do our synthetic division. And we see that 1 is indeed a root, or a 0. So now we're left with 6, 11, and -10 as our remaining factors, or our remaining polynomial. So looking at my roots, this looks like it's about halfway between -2 and 3. So I'm looking for a -2.5, which we have right here. So let's test and see if that is going to work there. Okay, we already found that +1 was a root. Let's test this -5/2. Okay, and again, we want to use that last row of our last synthetic division. Okay, if we don't do that, we're going to have trouble finding any irrational or complex roots later on down the problem. All right, so -5/2 is also a root. Okay, so now if we want to find that last root, we're down to a linear polynomial here. We just set that equal to 0 and solve. Simplify to 2/3. Check, make sure that lines up with our graph, and that could definitely be 2/3 right there on our graph. Okay, so we found all of our real roots. So now let's go and make sure that we answered what the problem asked us to do. Okay, so we were asked to list all the possible rational zeros of the function. So let's make sure we list those out. Okay, so we have 1, -5/2, and 2/3. All right, so we talked about how to use long division and synthetic division to find the factors of a polynomial in standard form. We talked about how to find the remainder of a polynomial in division using the remainder theorem, how to use the factor theorem to determine if a given factor is indeed a factor without actually doing division. And then we looked at either being given an equation or an equation in a graph in standard form and finding all of the real rational roots.